Welcome guys, Zaki here from KhanAcademy.com, and today we're finally finishing off Chapter 7 with 7.6, or the applications of the dot and cross product. So, if you're wondering what the applications are, there's many. For example, let's say you want to find the torque of a wrench that's being tightened or loosened. You can do that by various applications of the dot and cross product, as we'll find out later on. The same goes for if you want to find, for example, the amount of work being done when you push down on the pedals of a bicycle. Another nice little application of the products is you can find the volume of this shape right here called a parallelepiped, and we will also see that as we go along. So without further ado, let's move on to some tips that will probably help you out in this lesson. So we need to understand a few things before we even get started. First of all, diagrams will be your best friend. I cannot stress this enough, but lots of questions may seem abstract if you just read them out loud, but if you draw a diagram, you have already completed half the question. You're going to love me for this, but you need to do this. You need to draw diagrams. They will help you out so much. A second thing you need to understand is that section 7.6 is the last section of all of chapter 7. This is a culmination of all of the formulas and skills that you have learned, so you need to make sure you understand all of these formulas and practice the vector rules like addition, subtraction, and especially dot multiplication and cross multiplication, because they will be vital tools in helping us solve the questions in this section. You also need to understand some basic rules like how to turn a pair of coordinates into a vector, and understand the other rules as well, like the right hand rule. If you remember the right hand rule where you have to curl your fingers or upside down, this rule would be very important as well. So let's move on to a warm-up question to help you guys prepare for what's to come. Okay guys, so let's take a look at a sample warm-up question. And this is a very common question one might get in this type of vectors unit. So it's basically asking us to find the work done in the direction of travel. Don't be alarmed or intimidated, because all this really means is you just have to multiply these two, and as we will see. In order to find work, we just have to multiply the magnitudes of these, which really just means we are doing dot multiplication of these two. So I hope you guys have been practicing your dot multiplication, because it'll come in handy with doing this. So in order to do dot multiplication, we just do 200 times 2 plus 150 times minus 1 plus 75 times 8. And as you can see, that's exactly that. And if we add all that up, we get 850 joules. Just very simple, and this is the type of calculations you will be doing in the coming questions. So let's move on to our first problem. Alright guys, so let's take a look at this classic problem. So we have a wrench here being used to tighten a bolt. A force of 60 newtons is applied in a clockwise direction at 80 degrees to the handle, 20 centimeters from the center of the bolt. We are asked to calculate the magnitude of the torque, and in what direction does the torque vector point. So remember what I said, we can use the application of cross and dot vectors in finding torque? Well, this is exactly it. This is a classic example of that. So when looking at this question, if you just looked at it visually, you'd probably not be able to understand what's going on here. But that's why it helps if you draw a diagram like there is right here. Well, this diagram shows us that this is the wrench, this is the bolt. We see that the displacement of the wrench is 20 centimeters. So vector R is 20 centimeters. We also see the force vector. So the force vector, and it tells us the magnitude of 60 newtons. And we also see the angle being formed between them, which is 80 degrees. So, a couple of things to note here about finding torque. Whenever you see a measurement in centimeters, convert it to meters. Why? Because torque is measured in Newton meters. And we can see here, this is Newton centimeters. So that's not right. Now that you got that out of the way, 20 centimeters would be equal to 0.2 meters. And now let's get started. So in order to find torque, we usually represent it with the Greek tau symbol, and the way to calculate it, and from now on you can just call this the t vector. You can just say vector t equals the magnitude of r, so the displacement vector, times the force vector, the magnitude of that, times sine of the angle that they give you, and they gave you 80 degrees. So if we plug all that in, remember our r value was 0.2, and just to confirm that with you guys, I'll just show you again. This is 0.2. this is 60 newtons, and this is 80. So we have all of our values right here. We just need to draw the diagram to understand how to use them. So plugging all these values in, we have 0.2 times 60 times sine of 80. And if we plug all that in, we get 11.8 Newton meters. And that's it. Now in part B, it asks, what direction does the torque vector point? Well, if you remember your right hand rule, you would need to place your right hand on top of the wrench, and you would need to curl up your hands in such a way that it joins up with the force vector. The only way you can do this is by flipping it upside down and then curling it. But remember, when you flip your hand upside down, that means that the direction is pointing down. What does that mean? In the context of this question, it means that the wrench is being pointed downward into the material, meaning it's currently being tightened. So this is what I'm trying to tell you guys. Understand your formulas, make sure you draw your diagrams, and you'll basically be able to solve these questions. The wording can get a little confusing, but just make sure to practice these types of questions. Moving on. Alright, in our next problem we have a classic work problem, and see what I did there? So we have to determine the work done by gravity in causing a 45 kilogram child to slide down a 55 meter slope which has an angle of 47 degrees to the horizontal. Now if that went over your head, it will probably went over my head as well, but this is why I said you have to draw a diagram labeling all of this, and that will help you so much. So this is the diagram, and you might be wondering what all this means. So first let's deal with the mass part, the force part. So you're probably wondering how I got this 441. Well, in order to calculate the force, you have to multiply the mass times 9.8. So the mass given to us in the question is 45. So if you multiply 45 by 9.8, you get 441. This is a nice little physics application. So if you know physics, you'll feel right at home. But if not, just remember, take the mass, multiply it by 9.8, and you'll get the force. So that's how I got the 441 here. And this is the magnitude of the slide. So it's the length of the slide. So it's 55 meters, and that's how I got that. So this dotted line, it represents the horizontal. So whenever it says horizontal, imagine an imaginary x-axis. And if it's saying 47 degrees to the horizontal, it's saying 47 degrees to this imaginary line. So that's how this 47 degrees was arrived. And if you notice, this imaginary x-axis creates a 90-degree triangle. So 90, 47, we can find the remaining angle which connects between this vector, and this will help us so much. So we have to determine the work, and if you remember from our warm-up activity, determining work is just the magnitude of F times S. And our magnitudes was 441, 55, and we multiply it by the cos of the angle in between. In this case, that was 43. If we plug all that in, we get 1,738.98 Newton meters. See, all you have to do is understand dot multiplication, and this becomes a lot easier. Moving on to problem number 3. So a new application of these product, the dot product and cross product, is finding the volume of this 3D shape right here called a parallelepiped. And if you've been exposed to the triple scalar product in the last lessons, this is a good application of just that, as you can see right here. So let's say you're given these vectors u, v, and w. Well, to find the volume of this shape, you would need to do w dot u times cross v. So let's apply that with this example. So we're given the coordinates a, b, and c, and we're asked to find the volume of the parallelepiped formed by it. So, as we know, the volume of this will be formed by doing the vector a dot b cross vector c. So we plug all of our coordinates in, and this is what we have. So as we can see, this is our vector a, this is the coordinates of our vector b, and this is our coordinates of our vector c. Now, in order to do this, we have to do the cross vector multiplication first. So b cross c, we have to do that first. We cannot do a dot b. We cannot do that first. Just trust me on this one. We have to do B times C. So that's what we're doing. And in order to do uh, the cross product, remember the rule of writing the y coordinate underneath the b, the z coordinate underneath the b, the x coordinate underneath the b, and then back to the y coordinate. And this will make much more sense if you guys have practiced your uh, cross product for vectors. This will be a lot easier to do. But that's basically what we're doing. This is the cross product, and this is again just vector A. We're waiting to multiply the result of this. So after doing all of this, we get negative 93, negative 17, and negative 30. And now we can do dot multiplication. So dot multiplication is simple. Just take the x's, take the y's, and take the z's and multiply them by each other and add them up. And if we do all that, we get a volume of negative 549. But there is a catch. The volume is always the absolute value of this. So therefore, the volume is 549 units cubed. This will all make so much more sense if you guys practice your cross product, and you also understand all of these right-hand vector rules and all of the other rules, because finding this shape is going to be a lot more easier with the understanding of these rules. So the one thing to take away from this all is diagrams are your best friend for solving these types of questions, and remember to have all of these vector rules understood so that you actually know when to use cross multiplication, for example, cross product or dot multiplication. So yeah, that's pretty much the end of it. So thank you guys for tuning in. Bye.